Hello guys, I am Vaishali Kikan from Dopamine and we are discussing VLSI technology. In VLSI technology, we are discussing the CMP and today we are going to discuss the necessity, advantages and the applications of this CMP process. So without wasting any time, let's discuss the necessity of CMP. CMP is required for a lot of parameters. So let's discuss the various parameters because of which I am saying CMP is a necessary process. Now the photolithography resolution is given by the formula R is equal to K1Z upon Na. Right. So now to improve this resolution, what we can do, either we can increase the numerical aperture or we reduce the wavelength. So both of these things are very difficult, right, for a high feature size process. Now depth of focus is given as K2Z upon 2Na square. Right, so now here from the both of the approaches we can understand to improve the resolution we have to reduce the depth of focus. As the depth of focus is reduced, we can get a better resolution and we can get the smaller feature size. Right, so you can see from here. Now, if I have the 2083 angstrom as a depth of focus, the feature size is 0.25 micrometer. Right, so feature size is higher, the depth of focus is higher. Right, so when I have a higher depth of focus, the feature size will be higher. Now, if I reduce the depth of focus to 1500 angstrom, the feature size will become 0.18 micrometer. Right, so we will be getting a better resolution, smaller feature size, better resolution if I reduce the depth of focus. We have assumed that the K1 is equal to K2 and the lambda, right, or Z is 248 nanometer. The wavelength has 248 nanometer for the deep UV. We have considered the deep UV case and numerical aperture as 0.6. So in that case, the depth of focus is the only parameter which is changing the resolution. Right. Next, we have the 0.25 micrometer pattern which requires roughness less than 2000 angstrom. Right. So roughness should be less than 2000 angstrom for a feature size 0.25 micrometer. Now only CMP can be used to achieve this kind of planarization. When the feature size is greater than 0.35 micrometer, we can use other planarization methods also that we have already discussed in the introductory video. Now coming to the advantages of CMP. The CMP is a planarization method which planarizes surface and which will be giving me higher resolution for the photolithography process. So photolithography process will be giving me higher resolution in a planar surface. So this is the first advantage of doing the planarization using the CMP. Will be getting better resolution, right? The planarized surface will eliminate the side wall thinning also. So side wall spacer problem which was there, it will be eliminated because of the planarized surface. Because of the poor CVD step coverage, the side wall spacer was formed and we can remove this problem. Right, so you can see the metal line thinning due to the dielectric step. Right, so here you can see this is a step, the dielectric step for the IMD layer, and here you can see the thinned out metal line because here we have a tapered dielectric deposition. Right, so the step over here is tapered and due to which this area is thinned. So we have the side wall thinning effect over here. Right. Now when I have the planarized dielectric surface, we are not having this metal line thinning effect. And when I have the metal line thinning effect, that time we can have the numerous problems including the speed issues as well. Right. So the CMP eliminates the requirement of excessive exposure and development to clear the thicker photoresist region due to the dielectric steps. Right. In the dielectric steps, we have the exposure step as well as the development step with the photoresist. So it eliminates the requirement of excessive exposure and the development to clear the thicker photoresist region due to the dielectric steps. And also this improves the resolution of via holes and also the metal line patterning process. Right. The second advantage is that we'll be getting uniform thin film deposition which reduce the required overetch time. Overetch time is reduced and also it reduces the chances of undercut or substrate losses as well. right? So you can see overexposure and overdevelopment process over here. You can see over here we have the possible CD loss due to the more exposure and development. So here you can see this photoresist is lost at the corner due to the more exposure and development, right? So this photoresist, you can see the color has not changed. This require more exposure and development, right? So this photoresist still require more exposure and development, but here what we are experiencing, we are experiencing CD loss. So why it is happening? Due to the uneven surface. When the surface could have been flat, that time this problem could not have arisen. This photoresist exposure problem could not have arisen. We require metal surface to be smoothened out or flattened out. So we have, for the rough surface, long over etch process, right? So here you can see, here we require longer over etch to remove this extra layer, right? So we require longer over etch process. If I have a flat surface, we have a shorter over etch, right? So you can see we have a very less over etch over here, right? So it's flat surface, photoresist would be even, there will be no over etch over here. Now coming back to the advantages, so CMP, as we have seen, it reduces the defect density, it improves the yield of the process, right? So it improves the yield of the overall VLSI fabrication process also. Why it is reducing the defect density, it is reducing the over etching also. So here we are not having the photoresist problem, photoresist exposure problems also. So it is reducing the process problems in thin film deposition, photolithography, also in etching, as I already told you. CMP also widens the IC chip design parameters also, right? The design parameters can also be now improved and widened out, and it can also introduce defects of its own. CMP can also have their own defects also, right? So we require appropriate post CMP cleaning, and we have a dedicated video on the post CMP cleaning for that. So now coming to the applications of CMP. The first application is the shallow trench isolation formation. When the shallow trench isolation is formed, it will be forming a rough surface on the wafer, but we require CMP now here. So dielectric layer planarization is done with the help of CMP for the pre-metallic dielectric and the intermetallic dielectric. For the tungsten plug formation also we require CMP. For the deep trench capacitor we require CMP, right? So you can see over here the CMP of the undoped silicate glass over here, CMP of the undoped silicate glass, CMP of the tungsten plug over here, CMP of the undoped silicate glass over here, again CMP of the undoped silicate glass over here. Now coming to the deep trench capacitor. Now here in the deep trench capacitor, we have a silicon substrate over which we have a heavily doped silicon and over which we have a pad oxide layer, right? So first of all, we are going to develop the nitride layer over it, and after that we'll be having a photoresist process over it. So photoresist development, photolithography full process will be happening. Photoresist development, then the mask, exposure, photoresist removal from here, photoresist etchback process, and here will be forming a trench over here with the photoresist. Now we'll be removing the nitride and the oxide from this trench, and then we'll be removing the photoresist also. Now we have made the trench, there is no requirement of photoresist, it is removed. Now we'll be making out a trench over here in the entire substrate, right? So you can see it's a deep trench that we have formed inside the silicon substrate, and then what we are going to do, we are going to do the doping, right? We can do the doping over here and we'll be making this structure doped, right? So with the help of the diffusion process or ion bombardment, we'll be doping this structure. So after that, we are going to again put a dielectric layer, right? So this dielectric layer is formed over the nitride layer and also over this heavily doped silicon surface, right? So after that, we can fill this trench with the polysilicon, and now here you can see this is a heavily doped silicon which will be acting as a capacitor, as a conductor, and also this is again a heavily doped silicon which is again a conductor. This polysilicon inside will be acting like a dielectric. So conductor, and in between dielectric, it is acting like a capacitor. So this is how we can form a deep trench capacitor. The extra polysilicon is now removed using the CMP process, right? So now after that, this layer of the dielectric is also removed from the surface. The nitride and the pad oxide layer are also removed, and thus we have formed the capacitor, deep trench capacitor. The CMP is also used for the copper interconnection. The copper interconnection, again we have the surface roughness. To make the surface flatten out, again we are going to use CMP. Now copper is very difficult to dry etch, so here we'll be using the dual Damascene's process. So here we'll be using the tungsten plug as a Damascene's process, right? It uses two dielectric etchback process, one via etch, another trench etch, right? So metal layers are deposited in the via holes and the trenches, and a metal CMP process will remove copper and tantalum barrier layers, right? So here in the removal of the copper, we are using a dual Damascene's process, right? So first of all, we will be using a via etching and then the trench etching. In the via etching, we are doing the deposition of the metal layer in the via holes and the trenches, and the metal CMP process will remove the copper and the tantalum barrier layer. So after the metal CMP process, we'll be having copper lines and plug embedded inside the dielectric layer. So there will be still copper line and plug inside the dielectric layer. So you can see the PECVD of the nitride. So over here you can see over the tungsten we have done the deposition of the nitride layer. After the nitride layer, we'll be having the undoped silicate glass layer, and after that we'll be having the etch stop nitride layer deposition. Again we'll be having a nitride layer deposition. Again we'll be having the undoped silicate glass layer, PECVD. Then we can use the photoresist over here. We can do the photoresist coating and heating. Then we'll be using a via mask. After the via mask, right, we'll be having the exposure and the development of the photoresist. After exposure and the development of photoresist, wherever we want to make the via holes, we'll be making over here the gaps in the photoresist. We'll be etching out the photoresist wherever we want to make the via holes, right? So after that we'll be etching out the undoped silicate glass, and we'll be stopping wherever we'll be having the nitride layer. So we'll be stopping on the nitride layer. We'll be stripping off the photoresist. Now we'll be having the via holes. Now we'll be again doing the photoresist coating. After photoresist coating, we'll be using the metal mask. This is the metal 1 mask. After that, again we are going to do the exposure and the development of the photoresist, and after that we are going to etch out the undoped silicate glass, also the nitride layer over here. This nitride is also etched out, the undoped silicate glass is etched out. Now we'll be stripping off the photoresist. You can see we have formed the via holes. Now we'll be depositing the tantalum and the barrier oxide layer, right? So we will be having the tantalum layer over here. After that we can deposit copper. After the copper, we'll be doing the CMP of the copper as well as tantalum. So here we'll be using the dual Damascene's process to do the CMP, right? So to remove the copper, dual Damascene's process is used over here, right? So tantalum as well as copper is removed over here, right? Then we'll again do the PECVD, plasma enhanced chemical vapor deposition, and we'll seal this structure with the nitride. So I hope you understood why we are using the CMP process. If you want to do the further analysis, you can refer these books. Very amazing books these are. So I hope you like this video. If you like it, please push the like button, subscribe to the channel, share it with your friends, and also give me your feedback. And also don't forget to download our mobile app. Link is present in the description box below. Do meet me soon in the next class. Bye bye. Take care. Thank you.